My name is Adedotun Akintayo, and I'm a graduate student in mechanical engineering, Iowa State University. And I'll be presenting our joint work with, as you can see, all the other departments on high throughput. Basically, it deals with the high throughput phenotyping for detecting soybean cyst nematode eggs on microscopic image frames. So my talk today is pretty dense, and then I'm going to try to compress it as much as possible. But basically, I'll be trying to relate my topic to the workshop on food and energy, and then quickly I would also walk us through the algorithm design, and then the implementation. Followed by that, I'll show the results, and then where we plan to move it from here. So soybean is a major cash crop generator, cash crop export for the United States, with over 30 states producing into soybean farming. But with the advantages shown here, or the major uses shown, there are many yield reducers for the soybean yield, basically. And they are classified, some of them are classified as yield robbers. And amongst them, we found out that we could actually phenotype the pests, like under the soil management practices. So basically, soybean cyst nematode pest leads to about 100% yield loss in soybean yields, basically. And some people have analyzed that it leads to lots of revenue loss as well. And you can see on the right, well, there are examples of the egg on the left, and then on the right, you see how it has grown from 1957 in about 5 states to so many states, including the islands of Hawaii and Puerto Rico. Excuse me. So today, what they do is that they go to the field and then collect soil samples, and then they do the sample preparation, and something skipped off there. So basically, after preparing the samples, they add the Fushin dyes in order to color it, and then they take the microscopic images or the frames. And so today they still do manual counting, but what we looked at is, can we design a deep learning architecture to basically learn the features of the egg in order to like detect the eggs and then ultimately quantify the eggs on the frames. So we were told by the experts, the farmers and pathologists, that many computer vision approaches have been tried and they have failed, so they are not reported in literature. However, there is an introduction to the extraction by a master's thesis at the University of Illinois Urbana-Champaign, where the A. coded and crafted basically features of the eggs, which are the shape, the colors, and the size. And then it was able to come up with within 10% of expert counts on the problem. However, we noticed that there's sign defects, of course, of the eggs, like the arrow shown, where the sizes of the eggs or the features vary. And so we need something that's basically more automated than that in order to learn those variety of features. So what that shows to us is that there's variety of features which cannot be captured by that code. On the other hand, some other engineers designed like a semi-automated kind of approach where they would basically do a background-foreground separation, and then using a click style and to separate the foreground, which are the eggs, from the background, other debris and other things. However, that's still costly and inefficient, basically, because they have to do the clicking and clicking. So we still looked at that and said that, okay, can we get those images and the labels, which they already have, and then train the deep network, which we know already that learns rich features, to basically do the task for us. So we just run the algorithm, go to bed, and get the results next day, hopefully. So here's what we designed, a network we designed to do the work of the detection, basically, the first part of the problem. I'll quickly run through the network in bits, the major part of the network. So we can think about if we have an input data set, and then basically what we want to do is we want to learn the joint features or the joint weights that characterizes the network. However, to do that, we need to select filters. Moving on, the first layer is for a convolutional autoencoder is the convolution layer. So how do we do that? We put the filter on the image, like on the local neighbor of the image, and then we get the filtered image from that. We continue that, and then we also get the second filtered image. Continuing in that same manner, we filter all the image, and then that's the first layer, basically. After that, we move to the subsampling layer, where basically we get a maximum of the local neighbor in a local neighborhood for this case, but there are other methods for subsampling as well. And then by that, we transform the image to a max pool kind of image as well. Then the next layer, the next important layer is the fully connected layer, where we reshape the images we vectorize it basically, and then we encode those images, pretty much like discarding other debris in that coding layer. We add to that, we reshape it, we decode it to another vectorized form, and then we reshape it back to original images. And so that forms the core part of the network, which you're seeing here again. So how do we do the training? We take the input images, and then we add what we call the selectivity criterion, which is basically, any post-centered image is allowed, any post-centered egg is allowed, while other eggs which are not post-centered are not allowed, though they're still eggs. So that also includes the debris as well. And then we train the network using a backpropagation kind of algorithm, which is popular out there. And so after the training, we pass the network to a testing phase where we get new data set, out of sample data set, and then see if the algorithm performs well on those as well. So here are some features showing how the algorithm performs, how it goes through the hierarchical layers. You could actually see how the eggs becomes shown. That should be obvious. But what's interesting for us is that an egg which is not post-centered, the algorithm learns to discard it as well. And it also discards the debris as seen from the first one. So it's able to achieve good results, basically. Excuse me. So I also show some results for two extreme cases. In the first case, the algorithm is able to basically show the eggs, all the eggs, it detects all the eggs and discards the debris. And then in the second case, we have similarities with the debris, still have some similarities with the debris of the eggs, and the eggs, basically. And so the algorithm finds some misses and then some false alarms, basically. But that's in a few frames. And I'll show further results here. In 100 frames, the analysis is that the algorithm is able to recall 100%, but maybe that would be explained by the next point here, that the alarm rate is almost equivalent to the misses as well. So then its recall is 100%. And farmers are interested in the 100% because basically that shows that they don't apply more or less pest control. While from the algorithm standpoint, we're more interested in how precise our algorithm is. So we still find that our algorithm would be 96% precise. And so it still needs to be improved upon, basically. And the frame rate is also shown on the bottom. So here we have come up with a high-throughput end-to-end type egg detection algorithm, and which uses a selectivity criterion for training. And we have been able to achieve improved accuracy based on what's on ground. They are 10%, and we are like less than 4% within expert count. And then what we hope to, well, we counted those manually, but we have actually moved to the quantification stage, but since it was not in the paper, it's not reported. We've actually quantified it, and then the next thing is to try to test the robustness of our algorithm on other rare egg detection kind of problems. And using last year's model, we're given new set of data to also quantify on. And here are some of the statistics we have lately, which we are still improving on for your consumption. Thank you for listening, and any questions entertained.
The question was, how large was your training data set?
Our training data set was about 800,000.
Okay.
But that's from, so we had all these frames that were like 644, and then we could actually get small patches from that. So that's what made it about 800,000. Usually the algorithms require like big data to learn the different features and then generalize.
Thank you.
Thank you, too.
You develop a method to count things from an image. How easy is to make this method general to count any other thing in agriculture from that biological perspective?
Well, yeah, I think it should be fairly easy to count objects which you're interested in. But however, in this particular work, we have not included the counting stage. We did it just manually by looking after the detection. But with some algorithms which our other lab, our colleagues have developed, it's fairly easy to do countings of foreground objects.